Hey guys, I want to talk today about the harmonic oscillator, and I'll write Schrodinger time-independent Schrodinger equation at the beginning, and I'll solve this equation, and I'll find the wave functions that can identify the probability of the particle to be deposited at some space point. And let's start from the solution of Schrodinger equation. Minus s squared 2m, and when in the period when I write this equation, I'll give some additional information. The problem of quantum oscillator is enough important problem within the quantum mechanics because it defines the energy states of different atoms, and the spectra of systems are described using this simple model and some additional and using this model we can build some additional models that can identify the spectra. And let's imagine the system of atoms. They are deposited within some lattice, and they realize some oscillations or vibrations, and these vibrations can be measured by some light, and they have energy states of this, and this light can be absorbed, and the frequency of the light will be absorbed, identify the frequency omega squared c that can characterize the property of this measure. And that's why this question and this task of the solution of this problem is enough important. And I select the harmonic potential as in comparison with the classical mechanic. The harmonic potential has the following form. And if we will consider some structure of the following form where the body comes in this direction, we will have some comparable form. And in this case, atom can have the possibility to move here, and there is some returning force that can be proportional to some constant k and aim of this atom. And this force that returns this body to the backside is determined by some spring, but it is not the usual spring. The classical mechanics is a spring determined by the forces from surrounding atoms. The tension spring is determined by the energy of the atom wants to leave this position. But there is a forces of attraction, and that's why he can change his position at some distance, then he comes back. And it's some classical point of view that can represent the idea of using this potential. And I want to say that quantum mechanics and classical mechanics are connected with the rules of symmetry. That's why the result from quantum mechanics follows to the classical mechanics, and classical mechanics helps us to gain a result for the quantum mechanics. And all problems with the quantum mechanics start from the solution of this equation. It's only, and at this stage we have finalized the application of physics. For example, it's our first term of the second derivative, and it's our energy spectra, and it's our potential. And so it's a common form of our Schrodinger equation, and if we want to solve the apple, we can change this potential by the another and describe some more difficult motion. But now I want to solve such equation and make some changes. And if I can mention that we see is our frequency that is comparable to the frequency from the usual oscillator in a classical mechanics, and this rule symmetry is very often applied within this task. But let's continue. Let's make some substitution and let's write that y is equal m wc Planck constants and 2 and x. This is done only for writing this equation in a much more convenient form. And let's mark that there is another constant to Planck constants as omega c. And you want to understand why I apply this substitution. It's not clear always. Why people make so? Why they select y some new variables independent from x instead from? Strange. It's not clear. And now there is the main law. Physics and physicists are very lazy people. They don't want to work very much. They want to solve simple equations. That's why they realize different theories that can help them to solve very simple equations. Because there are mathematicians that can solve difficult equations, but the physics can build some model and solve only very simple. And let's make some assumptions that we have the infinite y after my substitution. And this substitution lets us to integrate this equation with this term. It's a constant. And to rewrite it in the following form: plus the neglected term is 0 is equal minus y squared u equals 0. Then I'll try to find the solution of these equations in the following form: y with power n exponent minus y and squared, and why we find the solution in the following form. The question is connected with this term. In addition, the solution at the infinity should be converted to 0. I mean the limits of this wave function as infinity should equal 0. This way we will have very unreachable from physical point of view results. That is this here we will have exponent. And the squares can be understood that we have the convergence for negative and positive values of this y. And that's why these equations let's find the second derivative of this function. The first derivative lets us rewrite this term as follows. Let's take derivatives from this one. For the first moment, it's important to find the first derivative because the second derivatives can be found as from the first derivative. It's y n minus 1 n exponent minus y squared 2 plus y power n exponent minus y squared 2 and the derivative from this unit minus y 2 and I have found the derivative from this function. And let's rewrite it in the following form: y minus 1 n minus plus 1, and let's find the derivative from this function. Is equals derivative from the exponent minus y minus y we don't make something with this unit. Plus exponent minus and the derivative from this unit. And the final form can be written in this way. Oh, excuse me, I have carried out minus 2 and minus 1 minus n and plus 1. My future. Exponent. Let's take its brackets, right before brackets, and in the brackets we have the following representation of this following terms: plus y n minus 2 n minus 1 minus y and plus 1. Well, and we have supposed that y extends to infinity. That's why we can neglect by all terms within this member, and the second derivatives can be approximately equal to the exponent with power y2 and multiplication y. And let's make some further calculations, and let's take the derivative that can help us to rewrite the following equation in the much more convenient form. And let's find the second derivative, but for the first moment we must find the first derivative. Okay, and let's start it. First derivative equals the derivative from the first unit here, h from y, exponent power minus exponent y squared divided by 2 plus h y and the derivative from the exponent minus y divided by 2 exponent minus squared y squared divided by 2. And let's take the exponent as a common multiplication term, and let's rewrite this expression in the following form: exponent minus squared y divided by 2 brackets h from y plus minus y divided by 2 h y, and so close the bracket, and let's find the second derivative, and the second derivative can be found with the same rule. We'll find the derivative from the exponent at the beginning, as there are two terms: exponent minus y squared divided by 2 minus y. Oh, excuse me, I have done some mistake here. There are no exponents, there are no division by 2, because we have the power of y squared, and we have the term within these exponents, of course, with 2. And let's continue. The same brackets plus the derivative from this unit and the same exponent. This exponent is a very interesting function. When we will define the derivatives, we always save these exponents. Second derivative from this term, h from y minus h from y minus y h from y derivative. And let's collect all the terms in the first bracket that are here and in the second bracket. Then it can be rewritten in the following form: exponent minus y squared 2 minus y h from y minus y h from y plus a second derivative from h minus h from y minus y h first derivative from y. And is all equals. And let's collect the terms. Exponents without any changes. When you have deal with the quantum mechanics, you have to solve enough difficult mathematical equations, because the problem of quantum mechanics finishes when we have written the differential equation of Schrödinger differential equation. So other problems I can actually only with the solution of the different differential equations. And let's take this unit and let's rewrite it in the following form: second derivative from y plus minus two terms with y and the first derivative from this function of h plus y squared h minus h from y and this all equals, and let us to take the second derivative and rewrite the mentioned above equations that you have already forgotten during the time of my different permutations. And so let's take this equation and control and rewrite it for the first second derivative. It's our second derivative, and let's write let's y squared 2 without changes take the form as h plus y squared h y minus h from y. And in addition, I have the following term: y squared u minus y squared h, and all. Exponent I have taken before the brackets. And now these terms we send them away. And of course we have this alpha, I have forgotten it, excuse me, plus alpha h. these terms we cut these terms, and the final equation that can be solved can be written in the following form: plus half minus 1 h equals 0. It seems to me not enough, everything is clear, but now I'll take h in the following form: sum from p to the infinity from the following members. First derivative equals the same sum, but y with the power p minus 1 with power p. Second derivative equals the same blah blah blah, and pi minus 1. It's the usual rule of finding the exponents. The derivative from the function was checked form. And we can rewrite this equation, and I'll mention here the most common methods of solution of such equation. We take p this sum and states here, but before I'll make it, I shall mention that we can't have negative powers from y, because if we will have such power, then when we have the limit for y to 0, we gain the infinity, and from the physical point of view, our function that was approximately chosen in the following form: a p exponents minus. It was selected because we can't solve the usual differential equations, and the physically imagined that we can use this substitution for the following solution. Can't have any problems when we have the limit to the infinity and to the 0. It means that we have the function describes some wave package that can't be infinity all as the whole space of our world. That's why within 0 and within the infinity, this function should be equals 0. That's why if we'll take the negative power, then we have some problem within 0, and this function goes to the infinity at this point, and if we will consider this case, it will be physically unreliable, and that's why we must use the another form of this second derivative, where we take the summation from 0 is impossible, and we take the summation from the second term, because if equals 0 and 1, then all these terms is going to the 0, because we have, of course, these units, and that's why we will rewrite the sum as plus 1 plus 2 times 3 summation from 0. And we have this unit, then make this function fall down for this, for all powers less than 2, for p1 and so on. And this all lets us to rewrite our equation. So let us rewrite our equation in the form sum p from 0 to the infinity, p plus 1, p plus 2, a, p plus 2, minus 2, 2 p plus 1 minus alpha AP YP with power P. I have missed some algebraic calculations because it seems to me it will help us to save some time. And the main idea of my activity is connected with the following step. I rewrite the connection of these members within this sum that was used in the common form as the solution of our Schrödinger equation, and we gain from here the rule that can give us the possibility to define the spectra of this system and the method of connection of unit of this sum. And from the first rule, and if we want to move further, we have to stay here. Alright, stop. And I want to attract your attention to this, to some first rule. Calculate permutations, calculation probabilities that will be done. Because everything that was done till this period of time was only usual mathematical calculations, and now we must think, what shall we do here? If at this period of time we have connected, we have gained a recurrence relation where we have connected two members of the sum, which is used for the substitution of function and for the first solution. But if we will take the limit of p to the infinity, then we will see that this member has the following dependence. And this sum from p y power p, when p streams to the infinity, streams to the exponents in the following power. We have, of course, the second exponent with minus with the power y squared 2 divided by 2. But after multiplication of these exponents at the infinity, we gain the following form of dependence when y streams to the infinity. What does it mean? It means that we have some physical and reliable solution, because, as mentioned below, we at the infinity wave function should equal to 0. It's our infinity point, for example, and here our function, because in another case the physical process will be unreliable and impossible, and that's why this condition can't let us to make further calculations. That's why we must take this sum and cut it for some p equals to n. Then we will not have any difficulties at the infinity. A from p, y p, exponents minus y squared divided by 2. Then we take this relation plus 1 minus alpha. Let's watch it much more attentively. And at some p that equals to n, this numerator equals to 0, and our alpha constants plus 12 plus 1 equals 0. And it is done only in attempt to terminate this sum at some member. This will give us the possibility don't have any difficulties as the infinity when we stream y to the infinity. And this gives us the relation for the spectra plus 1, because we take p equals 1, take this relation here, and then our relation is equal to 2n plus 1. Let's remember what does it mean with our alpha. It's 2 energy divided by Planck constancy and some frequency. And the frequency, and so 2m Planck constants equals 2n plus 1 energy equals 2n plus 1 Planck constants divided by 2. And from this condition we gain some spectra of the vibrating molecule within some lattice, as mentioned below, written, that can have some. This can make some oscillations at this point. And this energy levels are discrete, and the difference between these levels can be calculated using the relation n plus 1. Let's write it here. 2n plus 1 plus 1 minus 2n plus 1, this equals 2. This is energy difference between these levels is 2 multiplication the C H is Planck constants omega C. And the discrete and the difference is constant. For this unit, if we'll send some light, it can be absorbed at some energy level, causing much more serious vibrations, and it can define for us the matter of this material and substrate, because omega C is connected with the property of this matter, like the constant K divided by M powered to mass, and the constant K, which is connected with the media and the different properties of this material, because we have rewritten the potential and with this constant, as mentioned here we have the potential K, and this potential takes our molecule from this position to here from the classical point of view, and that's why this constant defines the structure of this material. If we will take, for example, the other atoms at much more distance, it's only example, then the K will be less than if they are near to this atom. And from different configurations and from much more basic theory, using this frequency and the spectrum, we can define the structure of this material. Of course, it's only some modeling case, but it can explain some fundamental ideas of such solution. And let's calculate our wave function. Oh, of course, I have mentioned that the sum that we have calculated have even and odd series, of course. The usual method of solution of such a question. We divide the sum for even and odd series starting from 0, a, so 0 coefficient and coefficient 1 coefficient. Let's rewrite the relation that connects the coefficients of the sum. Again, it's equals to p plus 1 minus alpha division p, make minus alpha, p plus 1, p plus 2. P plus 2, how are you? P plus 2, and find the first Hermitian function that equals this sum. P from 0 to n for this series, and P from 1 to the n for this series, starting from 1. As this division was not imaginable sum, idea is connected with the form of connection of these coefficients through the true number. And let's find the zero polynomial, or Hermitian polynomial. Each this polynomial equals p0, it's equals 1. We have selected a0 as 1 in this form. Because the sum only converges only for one term, and this a0, I have taken to 1. Let's find Hermitian polynomial 1. Each have the members a1, with in power of course in the power of unity, and it's equals and we select this number by our wish. And it's not so important because for us, because further we will have to use the rules. We will have to apply the normalization conditions for defining the final form of the function. But at this stage, I'll find only some of these Hermitian polynomials to have the formulas a1 plus a2 is power 2. a2, and let's take these relations for, and I want to connect a0 and a2. a2 p equals 0, a0 equals 1 minus 2 n minus 1 division by 2 minus n, and n is in our case minus 2. It means that the second Hermitian polynomials equals a0 minus 2 a0 y squared. But we don't like such form, and so in this case we multiply everything on the minus 2 unit for much more applicable form of writing this as a Hermitian polynomials as mentioned below. and we can multiply on every number. It doesn't influence the solution of our task, because further we will take these Hermitian polynomials and write the function in the form of Hermitian polynomials exponents, some constants that can be defined from the normalization rules. It can't be always clear for me why we take it in the following form. And that's why I will mention your attention that in every book it's written so. The first one is written as 8 third minus 12. Why? But let's write it to find the connection between A1 plus A3, A1, P equals 1, N equals 3, 1 plus 1, 2 plus 1, 2 plus 1 minus 2 multiplication 3 minus 1 minus 4, 3, 2 minus 2, 3, and A1, A3 equals A1 minus 2 divided by 3. And this third Hermitian polynomials should be taken in the following form: A1 y minus 2 divided by 3 is exponent, and we make the following form. We make the following: we multiply this member on the minus 6 minus 12. It lets us to write it as Hermitian polynomials. Or we can tell that we take here A1 minus 12 squared 8 minus 12. And let's make a last step and let's write our function h1 exponent minus figure 2. h1 equals, for example, y, some constants, of course. Normally this can be defined from normalizing conditions, exponents minus y squared by 2. This y equals here omega c h omega c Planck cos x omega c omega c Planck constant x, and the form of this function takes the following form: exponents minus omega c h x squared divided by 2. Let's write the normalizing condition for this function. The normalizing condition for this function have the following form: The solution of this integral demands the application of Gaussian integrals equations, and I'll not make it here, but I'll mention the most important features, that it is the probability of finding function somewhere within our area. And if we will solve this integral for this case, we can find that our function, wave function, have the following form. I'll rewrite it from the lesson book on quantum mechanics. Mass omega c h free exponents minus omega c h squared. And the common condition of its behavior is something like this, and this is our zero. When we grow the number of n, then we take the solution much more comparable with the classical probability of particles movement, which means when n streams to the infinity we gain usual classical unit, classical case. It's not maybe so clear, but you can memorize it now. And if we will consider, and from this method we can find all functions for different n, for different n. And the different n define these functions as and the probability of the particle to be displaced at some and some space distance. And as mentioned above, this theory helps us identify the structure of this material during the measurements of light absorption and the constant omega c, for example. And this omega c in usual equals 10 minus 6 radian per second. Okay, I hope this lesson will be useful for you. Quantum mechanics is not so difficult as you can see, but it demands some mathematical permutations, and of course I have missed some steps because I don't have enough time. But I tried to mention most important corners. I hope that quantum mechanics will be much more clear now for you. Thank you for your attention.